Okay. Amber pointed out and Hannah pointed it out again that somehow the sound was missing on one of my lectures, and I apologize for that. I don't know what went wrong. I think I start them the same every time, but that one had no sound. Okay, Amber, what were you going to...
I was going to say, is there sound running this time?
As far as I know.
Okay, I hope so.
I know, so the YouTube lecture is really not so useful. You can just look at the slide projection, progression.
It is if you write the notes, but you can't write the notes for homework.
Yeah.
So.
All right. We're going to continue by talking about chemistry here and chemical bonds. Now, last class period, I was lecturing about chemical bonds, and what were the types of chemical bonds we learned about?
Ionic, covalent.
Ionic, covalent. We just glossed right over metallic, right?
We took like one page of notes, or one slide of notes.
Okay, I was just saying, I didn't take pages of notes. And we talked about the covalent bonds have polar covalent bonds. What's the difference between a covalent, a polar covalent, and an ionic bond?
Ionic is a bond that we're like put in, so this table will only need one electron.
Okay, ionic bonds occur when we have two elements that have a large difference in electronegativity.
So a metal and a non-metal.
Maybe. Not necessarily. Depends on the metal and the non-metal.
Because
Yeah.
Yeah.
But it depends on the electronegativity. If you have an electronegativity difference of bigger than 2, it's considered ionic. If it's an electronegativity between 0.5 and 1.6, the difference is between 0.5 and 1.6, it's considered polar covalent. And if it's less than 0.5, it's considered non-polar covalent. It's kind of a continuum. And I actually have that slide. That'll be like 2 slides from now. I have 2 review slides there. But so that was all correct what you said. What I was looking for was the less insightful answer of an ionic bond is when you have something that has an ion, that is, it has an electronic charge that's not 0, something that's given up 1 or more electrons, something that has extra electrons, and are held together because of Coulombic force. Whereas covalent, what's a covalent bond? In contrast to that definition, where you have shared electrons. One didn't give it up, they're both sharing it. And then we have the one in between, polar covalent. They're still sharing the electron, but they're not sharing the electron equally. The electron spending more time with one than with the other. So here's that periodic table showing electronegativities, and we have the lowest electronegativity down the bottom left-hand corner, the highest electronegativity up in the top right-hand corner, not counting the noble gases. Yes?
On the exam, are you just going to give us like the periodic table, or are you going to tell us like, oh, it goes from this to this for biggest?
No, you'll have the periodic table that I gave you before that had the little legend that says this is where the atomic number is, this is where the atomic mass is, and that's the periodic table you'll have. So it gives you slightly more information than the one back there because it has a legend. And it's color-coded, but you'll have it in black and white, so you can't tell which ones are alkali earths and which one are alkali metals by the colors because it's in black and white. Good luck trying to decipher the different gray scales. So that's what you'll have. So you do have to remember the general trend that I'm outlining here for electronegativity and the general trend for sizes. So if we were looking at sizes, which are the smallest? What area is the smallest? Okay, so smallest, and where's the largest? So they actually kind of mirror, right? Except for helium is the smallest, so that continues on into the noble gases. So now we had like a transition metal or a metal with a non-metal. Well, here's an example of a metal with a non-metal. If I have iron and oxygen, the difference between those two electronegativities is about, 1.6? 1.6 is probably going to be considered a polar covalent. right? 2 is where we say it's definitely ionic. 1.6 to 2 is kind of indeterminate, but 1.6 would be covalent, polar covalent. So that would be an example where you'd say, probably polar covalent. If it was zinc and oxygen, or excuse me, not zinc and oxygen, copper and oxygen, well, it's a smaller difference, and so on. So it's not hard and fast. So here was our table summarizing how the electronegativities tell you if it's polar covalent, covalent, or ionic. These are bonds between atoms in a molecule. So reviewing that word molecule, what is a molecule? Okay, not the same, but a group of atoms that are held together as one unit. And so, for instance, a water molecule is H2O. One oxygen atom and 2 hydrogen atoms all bonded together with the types of bonds we've been talking about here, ionic bonds or covalent bonds, or metallic bond. Yeah. So that's what a molecule is. Today we're going to learn about bonds between molecules. This is something that's also important because we have something like a solid, something like ice. What holds ice together? Most of us probably never think about that. I know I would have never thought about that until chemistry. I just say, well, that's the phase. It's solid. H2O molecules are somehow being held to other H2O molecules. So there's some kind of force between molecules holding them together. Remember, forces are anything that push or pull. So there's something holding together. What were you going to say, Hosanna? And Hosanna knows the answer. So we're going to look into that for today's lecture. So now I can go into the new material. This is actually, these are not new either. There's 2 slides here, more that I forgot I had here. Molecular polarity. Polarity is when you have charge that is distributed in an uneven fashion. So one side's positive and one side's negative. This picture is trying to illustrate if you have a symmetry. In the case of carbon and oxygen, oxygen is more electronegative. Oxygen is going to want more electron charge. And so the covalent bonds between carbon and oxygen, how do I know they're covalent? Because I know that they have electronegativities that aren't that far apart. The covalent bonds are going to have an electron spending more time with oxygen, less time with carbon. And hence, as you can see in the picture, it has a plus there of the carbon. And the oxygens are pulling the electrons, so we have more negative charge on each left side and right side. So we have a net negative here, and positive in the center. But this is non-polar because it's symmetrical. So even though there is some charge separation here, it's symmetrical and it's non-polar. Whereas if I have something like the water molecule, once again, the oxygen really wants the electrons. So the oxygen has a negative charge. So that's why we have the delta minus, that's the negative charge. And the hydrogens have a plus charge because they're sharing electrons, but the oxygen is taking the bigger share and the hydrogen is taking the smaller share of the shared electrons. So this is polar with the bottom side positive, the top side negative. The bottom side being the side where the 2 hydrogens are. So here's water molecules. Now in steam, water molecules aren't bound to each other. They're flying around separately. In water, the water molecules are stuck together, but they can move around each other freely. And in ice, the water molecules are fixed in place. So ice, a solid, they're fixed in place. Water, a liquid, they can move around, but there is a general force holding them together. The general force, I believe, is simply still the reactions between these. But in ice, this is what you have. This is why ice forms a solid. You have, I'm going to change to black. You have an attraction between the positive hydrogen of one water molecule and the negative oxygen of another because they're polar. Remember, just like when you stuck the balloon to the wall, you had that dipole moment. That was inducing a dipole moment. In this case, you don't need to induce it. There's already another dipole moment. And so you have these bonds holding the molecules together. So that's why ice forms a solid. You slow them down enough, those bonds are strong enough to make them stay in place. You heat them up, they move faster, and they have enough energy to break free of the forces holding them in place. Now, here's a question that's kind of a non sequitur. This is making sure we understand molecules. This here, you notice it has the name written there, carbon dioxide. Using our rules, carbon dioxide because we can also make carbon monoxide. And H2O, dihydrogen monoxide, which no one ever says unless they're trying to fool you and talk about how dihydrogen monoxide is such a dangerous chemical. How many people have seen stuff talking about how dihydrogen monoxide is so dangerous? You know, and yet we all eat it and drink it, and the Food and Drug Administration hasn't banned it despite all of the deaths that occur because of it. Because it's necessary. And it's not really dangerous despite all the deaths that occur. There's lots of dangerous side effects from water. You can get water toxicity, but you need it. So, and it's not in any way dangerous in normal amounts. So the question is, which is heavier? So I want people to choose an answer and tell me why.
I was thinking carbon dioxide because the C is farther over on the periodic table. I'm guessing this is what you're talking about.
Yeah, and there's two oxygens.
Yeah, there's two oxygens. Oxygen is bigger than hydrogen, so
Okay, by bigger, you mean more massive.
more massive.
Yeah. And in fact, we can add these up. What's the mass of a carbon atom? It has 6 protons, has an atomic mass, and you would look back there to check, 12. So for the carbon dioxide, you have 12 atomic mass units for the carbon, and then you have 2 times the atomic mass of oxygen, which Hosanna tells us is 16. That's a 6.
Up there it says 15.999, but
No, actually it says 15.
We round it to the integer here. So 16 times 2 is 32, plus 40 atomic mass units of carbon dioxide. The mass for water, 2 times the mass of hydrogen, which is 1 atomic mass unit, plus 1 times the mass of oxygen, which is 16. So we have 2 times 1 is 2, plus 16 is 18. Oh, boy. Come back. Here we go.
So the U stands for units, right?
The U stands for atomic mass unit. When I was your age, we had to write AMU, but now they've decided to just use U instead of AMU.
So can we not write AMU? Because that's what I think I did on.
It's certainly going to be considered correct if you put AMU.
because when you get to stoichiometry, that means micro.
Actually, micro is this.
It looks the same.
No, this is a M. That's an M. It's a mu. Okay, so you understand how to do that. One of the points here was to make sure that people didn't answer, it depends. Right? It doesn't depend. A water molecule has exactly 1 oxygen, 2 hydrogens. Carbon dioxide, 1 carbon, 2 oxygens. So you can add them up and get their masses. Okay, now molecular attractions between molecules, will start with the ion dipole. An ion dipole is what is going on when we dissolve salt in water. By the way, salt is a term that covers more than just table salt. Sodium chloride is what we consider salt. That's table salt. And so that's what I called salt here. You see, I wrote the example as NaCl, sodium chloride. When you put sodium chloride crystals in water, because water is a polar molecule, the water will actually separate the sodium and have the negative oxygens form a bond with the positive sodium and have the negative chlorines form a bond with the positive hydrogens. So this is called an ion dipole. The sodium and chlorine are both ions. The dipoles were the water. It's an ion dipole bond. Now this is a bond between molecules, not a bond holding a molecule together. So we don't have a molecule that's sodium tri-water, right? It's just sodium that is being attracted by the oxygen sides of water, and chlorine that's being attracted by the hydrogen sides of water. And so that's what's going on when you dissolve salt in water. You're having the sodium is separating from the chlorine and being surrounded by the oxygen sides. The chlorine is being surrounded by the hydrogen sides.
But that's considered a chemical change.
It's a chemical change because you did have sodium being bound to chlorine, and now it's not bound to chlorine. So that's why it's a chemical change. It's good thinking there, Bryson. Okay, so that's our strongest of the bonds between molecules. Our second one is dipole-dipole. So that's an example here. We're showing the hydrogen bond, as Hosanna correctly named it, that's going on between, let's see, yes, this is a water molecule here, and another water molecule. And so you have an attraction between the positive hydrogen and the negative electron pair there in the water molecule. And that's a pretty strong force. As I said, that's the force that makes water stay together. And we'll see a comparison of boiling temperatures and see what difference it makes if we have these dipole-dipole forces. The next one, dipole-induced dipole. So we have to make sure we understand what induced dipole means. We've already seen it in our, that's the last lab. When you took those balloons and you rubbed them on your hair and you stuck them to the wall, the balloons stuck to the wall. Right? Otherwise, I wouldn't use the word stuck. Why did they stick to the wall? Because it induced a dipole. The wall did not have a dipole. The wall did not have, here's a positive side, here's a negative side. But when I brought the balloon up, the balloon had a, was it positive charge on it? And so that positive charge made little dipoles in the wall rotate or induce, okay, if they actually had dipoles, it would make them rotate. If it didn't have dipole, it can induce them. Because if I have something that's perfectly symmetric, like a hydrogen, or let's say a helium atom. Helium atoms are symmetric. If I bring a positive, it's going to push the electrons away from the positive. Actually, I said that wrong. It's going to pull the electrons toward the positive, isn't it? Because opposites attract. And so if I bring a helium atom close to a positive charge, the electrons are going to get pulled closer to the charge, and the nucleus is going to be repelled because it has a positive charge. But now I have an induced dipole. Now my helium is no longer symmetrical. It has the charge with one side more negative, one side more positive. And because the electric force is stronger when things are closer, the attractive force between the closer opposite charge is stronger than the repulsive force with the farther repulsive charge. So that its net force is it's going to be attracted. So you take something that has a dipole, you bring it close to something that doesn't have a dipole moment, and the charge in the thing that was originally nonpolar gets distorted so it becomes polar, and then you can have a dipole-dipole interaction. So that's what a dipole-induced dipole force is. So here's an example how would you write the chemical formula for this molecule in a box? O2, because it has 2 oxygens. And how would you name that? Okay, dioxide works. It does. We usually call it oxygen, but you can also have O3, and so dioxide is actually better to use than just oxygen because it's more distinct. But normally we just say ozone for O3 and dioxide, and oxygen for O2. So we bring it close to a water molecule, and these negative lobes in the water molecule are pushing the electrons. So the red is indicating where the electrons are hanging out, pushing the electrons so it's more negative on the side away from it. So this side's more positive. Positive is attracted to negative, and it holds them together. So that's a dipole, induced dipole force. And then our last one is induced dipole, induced dipole. And as you can imagine, that one must be really weak, because you start with 2 things that have their charge symmetrically distributed. You bring them close to each other. And so taking the example of argon is on the screen. Argon has the electron cloud out here. You bring them close together, and the electron cloud is going to get distorted so electrons move away, and the nucleus is closer. And one of them, okay, so let's say I have 2 argon. I'm going to take my right hand is one that I'm going to say, this one's unchanged. This one here comes in, and the electrons get moved away so it has more positive on this side. But then the electrons here are attracted to that positive. And what we end up doing is distorting both of them so that we're going to have them like this, so the negative and positive can bond together. Now that's super weak. How do we know it's super weak? Well, take the example we used. Argon is an inert gas. And we're using it as an example of how this kind of bond can work. If we consider it inert, it's got to be very, very weak. So if we look, and here you see just a number of them doing what I said. So if you look at the strengths of these, the strongest is the ion-dipole interaction. That is something like sodium with water. Water is an electric dipole. Sodium is an ion. There's going to be a strong force there. The next one, dipole-dipole. That's like water with water. Dipole-induced dipole, like water with oxygen. And finally, induced dipole, like the argon-argon example.
Like, what was the strongest level? What's the mixture you said?
The example I gave was like sodium with water.
And that's the like strongest?
Yeah, that's the strongest type.
I don't get why it's stronger though.
It's stronger because you already have charge separation in both cases, with one a distinct charge, right? Sodium, it's positive all around it. And then we bring the water molecule, which I'm going to do like this. The water has a net charge of 0. And so you're going to have, one would expect a net force of 0 with a net charge of 0. But because you have the charge separated, the charge that's closer is going to have a slightly stronger attractive force than the one that's farther away is repelling. So it's weak because you have a net charge of 0 on one of them. But because of the charge being separated, you still have a net force. Right? If it was a positive and negative, it would be a much, much stronger force. Because you would have the repulsion of the positive. So here is a good example of how this plays out. This is actual data, the boiling temperatures for different substances. And here we have 3 polar compounds: water, ammonia, and hydrogen fluoride. Just to make sure we've been following along, on hydrogen fluoride, which side is going to be the negative side of the hydrogen fluoride? It is the fluoride is the negative side because fluorine is our most electronegative atom. It's the one that wants electrons more than anything else. So anytime you have fluorine, it's going to be pulling electrons its way. Hydrogen is actually 2.2. It's pretty intermediate, but fluorine is about 4, so fluorine wants it much more. So the fluorine is going to be quite negative compared to the hydrogen, quite positive. What about ammonia? Which one wants the electrons more? The nitrogen or the hydrogen?
The nitrogen.
The nitrogen. And so the nitrogen is going to be the negative side, and the hydrogens are going to have a net positive. And ammonia is kind of shaped like a pyramid. So the 3 hydrogens are like the base of the pyramid, that's your positive side. And then the oxygen sitting on top is your negative side. And of course, water, kind of like a TP.
Why did fluoride compounds boil at a lot lower temperature?
That's the point of this. The point is that polar compounds are going to have dipole-dipole forces between them. Whereas nonpolar are just going to have induced dipole forces between them. So the dipole force is a stronger force, hence there's more force holding them together. You're going to have more kinetic energy in the atoms, i.e. a higher temperature, before you can break them apart. So that was the key.
So the polar ones have dipole-dipole,
Right.
and that's the weakest.
No, it's the second strongest.
Yeah.
And these down here will have induced dipole, which is the weakest. And so that's, it makes a big difference on their boiling temperatures and also on their freezing temperatures. Now, I don't even remember why this question comes up in the textbook at this point, but I kept it in because it's just kind of fun. Is it possible for a fish to drown?
Yes. Yes.
Okay. What does it mean for a fish to drown, by the way?
It was oxygen.
Yeah. My interpretation of drowning here is they suffocate. That's my interpretation here, because it's different for a fish than a human. Well, how does a fish normally, quote, breathe? How does it exchange oxygen? Okay, through its gills.
You bring the water through the gills and the fish extracts the oxygen.
Okay, brings water through the gills and extracts oxygen. Now, where's the oxygen coming from that it's extracting?
Water.
It's not water. That, which I assume is surprising to everybody, even though only 2 people expressed surprise.
Are there like air bubbles in the water?
Yes, there are air bubbles in the water.
Okay.
There are little tiny bubbles, not in your brain, that have air. And so it takes the water in and it pulls oxygen from those air bubbles. So it doesn't matter, the water's, I think this is right, 88.8% oxygen by mass, because the fish aren't breathing the O and the H2O. They're breathing the oxygen, the O2, that's in air bubbles. So
the answer would be D.
well, let's go through them individually, because I haven't analyzed them either. Number 1, fish breathe water. Well, no, they don't breathe water. It's that goes with C, saying that they'd be extracting oxygen from water itself. So then we have when the water contains too little oxygen, or when the water is not moving. There's a relation between those two. Anyone here have like fish tank or pet fish? Used to. Okay. What do you do to keep your fish from dying?
air bubbles.
You buy a little bubbler, or you can have plants because plants will also oxygenate the water. But the bubbler is the one that's easy to see. Now you see it just making bubbles, and you tend to think, I don't see why that's important. But not only is it making the bubbles you see, it's also giving off little tiny bubbles that are just being held in place by water. And so the water is filled with these little tiny bubbles. And then that's what the fish take in and breathe. Now we have the answer that Hosanna said, when the water is not moving. Well, in a natural case, in a pond or something, you don't have a little bubble. And the fish still live. In the pond, it must be because they have some kind of algae or something that's producing the oxygen bubbles for them. But if you have a stream, when you have the water flowing, you're actually going to have it bring in some water bubbles so it keeps it oxygenated. And so when the water is not moving, they can take out all the oxygen bubbles and there's nothing replacing it if you don't have something like a bubble or something else that's biologically producing water bubble or air bubbles. And so these two are related. I once again am finishing too early. I thought I had way too many slides, and obviously I was wrong.
Is that the last one?
I think so. No, I got one more after it. I was hoping I wouldn't get to the gecko one. Okay.
Yeah, can you make sure there's volume on it this time?
I always try to make sure there's volume. Okay, Teflon. Teflon is what we call a polymer. It is a chain molecule that's very long. It has carbons, a very long chain of carbon, and then connected to that carbon, each carbon you have 2 fluorine atoms. So the unit cell for Teflon is CF2 that's repeating over and over and over. And we use Teflon for nonstick coatings. And first and foremost, a lot of people get really concerned about, well, Teflon is a lot of fluorine. Fluorine is the most electronegative element. Fluorine is very caustic. When I was in graduate school, I used an excimer laser, excited dimers, and one of the gases I used was fluorine gas. And so when you're in science labs, they make you read the material safety data sheet to tell you about what you need to do to be safe. And when I read about the negative effects of fluorine, I was like, I don't want to get within 10 miles of this stuff. I mean, it's really brutal on your body. And yet we have Teflon in all of our pans, and we eat that stuff.
Yeah. It's a toothpaste fluoride.
Yes, and we put fluoride in toothpaste.
It's very bad. Wait, really?
Yeah.
Yeah. I have toothpaste in my backpack.
Oh yeah, it's
Unless
definitely.
you get fluoride dentist.
You have to actually specifically try to buy non-fluorine toothpaste.
Yeah, first ingredient, 0.243%. And 0.15% with, I don't know if that means fluoride ion.
That's why you don't
So,
polish.
I mean, I guess it's supposed to help like build up enamel and make your teeth stronger, but I don't know. I
Okay.
think it's a conspiracy.
It's a conspiracy. They're out to keep us from getting old.
That's why they a lot of times don't make kid toothpaste with it because they swallow it.
Yeah.
So it's never to not swallow it. That's
Yeah,
and then once
it
you, like,
literally
with
just
Tom's
said do
toothpaste,
not
like the
swallow.
little kids
Call
ones are all
poison
fluoride.
control.
Then you get to the adult ones and it's like has
When you go to the dentist when you're a kid, they'll do fluoride treatments where they
Yeah.
spray the foam inside of this and they put it up against your mouth. Or against your teeth.
That's horrible.
Well,
I loved it. It's like a cherry. Cherry grape flavor.
let's talk about this just a little. Now, I'm not a master, so you can't take everything I say on chemistry as like, that's the gospel. But, great. So, Teflon is largely fluorine, and we put that in our cooking stuff. And a lot of people do get concerned, as you guys expressed. But Teflon is virtually inert. You have the Teflon molecules here, the long polymer chains, they are non-polar molecules. So they are, and Teflon, the fluorine is really, really holding on to its electrons and holding on to that carbon. Your fluorine is not going to get away from the Teflon. And so the Teflon will go through you in the same manner as silicon dioxide, otherwise known as rock. It'll just go through you and won't interact with you chemically. Not the same as if you had fluorine directly going into you. Now with the toothpaste, there's actually reason, or fluoridated water. Almost all municipal water supplies are fluoridated to make your teeth stronger. Because your teeth, the enamel, I took a class, boy, it was just this last summer on this, and now I don't remember what the names of the chemicals are, but your teeth are strengthened when they have the fluorine to assimilate into the enamel. And so your teeth, believe it or not, you're constantly tearing down your teeth and they're rebuilding, which seems odd, right? You tend to think it's there, it's just solid. Things like, we'll learn about acids and bases, and acids will make your teeth susceptible. So if you take something acidic, like let's say a soda or orange juice or tomato juice, and then you brush your teeth, that's bad for your teeth because you're taking off part of the enamel. So the fluorine in fluoride toothpaste is there to help rebuild and strengthen your teeth after you've done things to damage them. And so there's a definite positive for your teeth. There's some people who are definitely worried about the negative of fluorine acting on your body in that case. And I'm not sure what the form is, but it has to be somewhat accessible if it's going to be assimilated into your teeth. Whereas with the Teflon, that fluorine is just not accessible. So Teflon, I do not believe poses any threat to health because the fluorine is going to stay stuck there. And the reason we use it for non-stick is because that Teflon is non-polar. The only kinds of bonds it could form with anything would be induced dipole. But because the fluorine has such a high electronegativity, it's not going to be very strongly induced dipole. So it's going to have very weak induced dipole. Now, yeah, it's not the last one. I actually had to look this up myself just to make sure I knew the answer. This is in your textbook, of course. Why do geckos' feet stay so clean? The answer is because the gecko's feet, like Teflon, are highly non-polar. They're things that are going to be hard to polarize. And so they're not going to form induced dipole bonds with stuff. So it puts its foot in dirt. The thing that is holding the dirt to things like your skin is an induced dipole thing. Or in the case of my body, since I have water all over the place in my body, I have the dipoles of the water interacting with the dirt, and that's what makes it stick. And since theirs are non-polar, it really doesn't stick. So they step on something else, there's going to be more attraction between the dirt and whatever they step on, and it stays there and leaves their feet. Is that cool? It's not physics, but it's still science, so I still find it absolutely intriguing. Okay, so to make sure we understand some things, we talked about 4 different types of molecular attractions. Which takes the least amount of energy to break apart? That's which one is the weakest?
D.
D.
Okay, so we have D is our answer from Amber. What do you say, Jessica?
I agree.
You agree?
It's
What, Hannah?
wait.
It's not any.
Yep. The least amount is induced. In fact, I put them here in order of strength. The strongest is this one. And the weakest is the induced dipole. Yes,
So
Amber?
what if our a PTQ is very similar to this because we didn't know you had this.
Same.
It's already like written down.
Almost word for word, maybe.
Yeah, almost word for word.
The bigger problem there is the two of you have the same question because that's going to lower your score.
Mine says this, John.
Well, yeah, this is different.
I
don't know about
Amber,
that.
I think all three of us have the same question.
No, mine is
I had the
we
same
guessed,
question as
but
them.
it's like the same.
We all have the same question.
Wait. I know you can't predict what other people are going to put down there.
Yeah. We have the same ones.
Mine's not.
What is the strongest kind?
All right. Well, while you're thinking about your questions,
We have to make up another one?
well,
Like that's
if more than one person has fundamentally the same question, that is what I use to lower the originality scores. Let's.
Wait, can we show you to see if we wait?
That was great.
Can we show you to see
No,
if
I
it's that
can't
close?
grade on the fly.
No, but like I'm serious, like because we worded it differently.
If they're fundamentally asking which is strongest, which is weakest, then they're fundamentally the same question. So
That's not fair. I don't agree with the grading system.
I'm sorry. I try to be very agreeable.
I hate this.
It says I'm already logged in. Yes, Amber, you have a question.
Number 9 on homework.
Okay, it's homework 6, right?
Yes.
So Amber wants to know about number 9. Assuming that there's sound going on, a radioisotope means that it is a radioactive nucleus. So a radioisotope is placed near a radiation detector which registers 80 counts per second. So that we call that the activity, by the way. The activity is how many decays per second are occurring. 8 hours later, the detector registers 5 counts per second. So how much is the activity dropped? We want it in factors of halves. So is it dropped by half?
Well, that's the thing. I don't get how to get it from 80 counts per second to 5 counts per second.
Okay, so let's cut in half.
By half 40, then by half again 20, then by half again 10, by half again 5.
Okay, so it's cut in half 4 times. And so since it's been cut in half 4 times, then how many half-lives has it gone through? 4. And so then we have how long it's been. It's been 8 hours. If 8 hours is 4 half-lives, how long is 1 half-life?
2.
And then oh, I'm laughing at option A for question 11.
That was a multiple choice question.
Wait, that was supposed to be multiple choice?
Well, no, each one.
You have to say
Yeah.
So is grape juice turning to wine? Is that chemical?
chemical. It's chemical, physical, chemical.
Okay, why?
Because hold on. Where's my
D isn't
Alcohol
chemical though, is it? D isn't
D is
chemical.
D is chemical. There's only one physical, which is C.
Yeah.
Wait,
Because when you eat food, that like gets changed. And like, or the nutrients in your body, and then it goes
How does
to
food-
like,
What?
wait,
Okay.
is D chemical?
Food and like
Yes, the broken leg membrane itself is chemical because you are taking
See, I'm smart.
calcium
My brain
and
just
other
goes like this.
minerals and nutrients from the food and processing it, and then you're creating a new chemical there to make the bone. Right, and it's a new chemical. It's the same atoms, but they're being assimilated into a new chemical.
But that's eating, that's not a broken leg in itself.
Well, the broken leg healing, you have calcium ends here, and then you add more calcium, and you add whatever it takes to make the blood vessels. Those are all making molecules.
But even if we're correct and we describe why we thought it was correct, we still didn't correct.
Incorrect.
You have to have your reasoning Make sure you have your reasoning for each one.
Yeah, it says if you are incorrect in your assessment, you should be able to defend why you chose that.
Is 74 H2S?
Okay, what is the chemical formula for the compound dihydrogen sulfide? So we're just going to take our rules. So what does di mean? What does di mean? Two.
What the heck, man? I am smart. I just keep answering these.
So that means we have two hydrogens. To indicate two hydrogens, we put a subscript of 2 after it. And then we have sulfide, so H subscript 2, S.
Can you explain something?
I can explain.
Right on the homework, but my brain doesn't reflect it.
Did you explain how you got there?
Yeah.
Okay. Because that's the biggest thing. If you just put H2S and you don't have any reasoning, I can't give you credit.
Okay, well, what's your reasoning? Let's see if
My reasoning is that di means 2, hydrogen means H, sulfide means S. And so I have 2 hydrogens and a sulfur, so H2S.
Okay, I can see why I didn't watch.
All right. Have a great day. I'll see you for lab mañana, except for people who won't be here tomorrow. I guess.
There's the 4 of us.
Our whole table. We failed together.
I like to think we pass together. We succeed together.
Well, our table.
What's the lab like?
It's a chemistry lab.
Have a good spring break.
Thank you. You too.